So, as Daniele said, I want to talk about time in quantum gravity, and specifically about what is called the problem of time, or better, the problems of time. And in doing so, I hope to convince you that most of these problems, if not all, go away if, on one hand, the deep structure of space-time is discrete, and on the other hand, if one formulates quantum dynamics in the language of histories, or if you like, the language of the path integral. So what are these problems? Let me start by listing 6 of them. We'll give including the most important one, and giving a sort of sampling of what I mean by the problems of time. So the very first problem of time, I've called them here POTs, problems of time. The first problem of time, which is, I think, by far the most serious, and what people often refer to if they use the word in the singular, is the problem that in the canonical quantization of gravity, one ends up with a wave function that depends a priori, it depends a priori on a 3 geometry, which is the analog of a position. If you thought of a moving particle, this is a point in configuration space, this 3 geometry. So it's a geometry on a space-like hypersurface physically, and a time label a priori, but one finds that the dependence on the time label drops out, the so-called frozen formalism of quantum gravity. And this dropping out means that not only did you not have a space-time, you had only space, but you have a static space. You don't have a wave function evolving in time. It's as if you got out of the quantization procedure the time-independent Schrödinger equation when you were expecting and hoping to get the time-dependent Schrödinger equation. This is, I've called, just as an aside, I've called this a function of 3 geometry. There are other dual representations, loop states, and so on, but they have the same feature, that the time label disappears. So the problem of time in the first sense, which is specific to canonical quantum gravity, is that one needs to recover time, or if you like, recover space-time from a formalism that only really knows how to talk about space. Now, you might find this a little mysterious why this happened. I'll try to explain it a little later. If I had a little more, I weren't so pressed for time, I would say a little bit about the unimodular formulation of gravity, which to a certain very limited extent resolves this problem or lifts this problem. However, it turns out, when one considers it more closely, that it basically leaves everything as it is. It's, if those of you who know the language of a many-fingered time, it sort of it recovers one finger out of an infinite number. And except in the context of highly homogeneous space-times, as occur in Friedman, Robertson, Walker models, for example, or Bianchi models more generally, that one finger is far from enough. So I won't say anything more about it, unless someone wants to ask me later. So this problem of, this sort of original problem of time is what I've called here the most blatant, this frozen formalism. It's useful to try and understand why this came about, and in what sense. It's normally always identified as an effect of the diffeomorphism invariance of the theory, and it's useful to see in what way it's related to the diffeomorphism invariance. And then, having seen that, I'll say that other conceptual problems, or even technical problems that flow directly from the diffeomorphism invariant, can be regarded in a slightly more general sense as problems of time as well. So why does diffeomorphism invariance lead, or if you like, coordinate invariance, general covariance, all these are different names for the same thing. Why does this lead to this frozen formalism in which time has disappeared? Well, there's a standard way of proceeding using quantization of constrained systems. What happens at a formal level is that the Hamiltonian, which was supposed to generate time dependence, becomes what's called a constraint and just a condition on the initial data. And this is very well familiar to people who work in this. But to get a direct understanding, I think it's easier to refer back to the path integral. So what does a path integral do? There's two ways of thinking about it in the cosmological context. One of them is the one that you'll find not only in a cosmological context, and the one that you usually find in textbooks, and the one that corresponds fairly well to the description that George gave when he was talking about initial conditions and distinguished slicing and so on, is that one starts with an initial data given on a site. So this is the space-time here, represented in 2 dimensions. This M is the full space, or portion of the space-time. There must be some way to not have this happen, but I'm not sure what it is. Anyway, so there's some initial hypersurface here, represents initial, on which we would give a wave function that is a functional of the 3 geometry, for example. And we then want to propagate the wave function to a future boundary of this truncated space-time by doing a path integral, a sum over, attaching an amplitude to every metric that you can install in this intermediate region, and then maybe I should just point at it. Every metric that you every metric that you can install in this intermediate region, sum over all the amplitudes, and that'll give you the amplitude for the final 3 geometry.
The green, that one there, green.
This one?
Oops, it should be turned on.
Oh, I don't. It's all right. I don't. Okay, so so you sum over the amplitude, sum over the intervening or interpolating 4 geometries. That is gravitational fields, if you like, and after doing that sum, it gives you an amplitude for any given final 3 geometry. So this is a kind of what people call a propagator. Now, it's interesting that in the cosmological context, we can do something a little different, a little better, because here there's a question of how did we choose the initial state. However, in the context of cosmology, in which if we take the space-time to actually have a beginning, then we don't need to choose an initial state at all. Instead, we can choose a boundary condition on the 4 geometries, in other words, on the kind of space-times we're summing over. And a very natural boundary condition is that the universe should emerge from zero volume state and expand. Turns out there's a well-defined set of metrics that do this that come out of Morse theory. I won't talk about it. But the point for this purpose of this meeting, I think the interesting thing is that this provides an initial condition without, or of a different sort. It's not a condition on the wave function, but it's a condition directly on the histories or on the space-times. So it gives us, in principle, the kind of, I forget what it was, David had some special word for this initial time. Past hypothesis, right. The past hypothesis in this case would be that that the early universe expanded in this particular way from zero volume. This is closely connected, but not the same as what's called the Hartle-Hawking prescription. The difference being that in the Hartle-Hawking one uses imaginary time, and this is using a real Lorentzian time, but it's otherwise closely analogous, although the technical difference is important and can lead to dramatically different predictions. Okay, so but our question here is, why does this path integral produce a frozen time, a wave function that doesn't depend on time? So in a general quantum theory, even in particle mechanics or quantum field theory, what the Hamiltonian does is it moves the final boundary or the final endpoint of the world line you're talking about in the case of particle mechanics. It moves it forward or backward in time. In other words, it tells you how the wave function changes when you move the final boundary forward or past, or more general, deform it in some sort of wavy way, but you can move it forward in some places and past in other places. But now if we take into account diffeomorphism invariance, then we can conclude that the effect of moving the boundary is really pure gauge. In other words, all we're doing, if we move this boundary, we're just creating a slightly different manifold. It's as if we just change the coordinatization of the manifold. But when we come to do the path integral, we sum over all possible four geometries. And summing over all possible four geometries on a manifold which is slightly extended towards the future is the same thing as summing over all possible four geometries on the original manifold. Therefore, the wave function that it produces doesn't change. Since the Hamiltonian is that which generates the change of the wave function, the Hamiltonian must annihilate the wave function, and that's the frozen formalism. Okay, so the variation under this of the wave function under the deformation of this final hypersurface is zero, and therefore the Hamiltonian which generates it must be zero. So that's the origin, from a path integral way of looking at it, of the frozen formalism. And one sees that it arises directly from diffeomorphism invariance. So in a more general sense, we can call problems springing from diffeomorphism invariance problems of time. One sees this directly. Diffeomorphism invariance corresponds also to invariance under how you foliate the space-time, and that makes it look even more directly as a problem of time. So the second problem of time, or set of problems of time that I want to look at, is problems springing from diffeomorphism invariance, or general covariance, if you like. Yes?
Let me just make sure I understand this, because it seems like an important point. So the trouble is something like, because of the content of diffeomorphism invariance is that the formalism doesn't know how to distinguish between us pushing ahead in time and us just recoordinating
exactly, yeah.
the block of space-time that we already had.
That's right. That's exactly right.
Good, thank you.
So, among these subsidiary, this other set of problems, we can distinguish in a very rough way problems of principle and problems that are technical, although it's notoriously difficult in the quantum gravity game to make that a precise distinction. You're never sure whether something that looks like a problem that's just technical might really be disguising a problem of principle. But anyway, that's not important, exactly how we categorize them. So let me discuss one key problem of principle and then a couple of equally key technical problems. So the problem of principle I've called here the problem of finding observables, or any other word that you like that's instead of observables, like beable or variable. What it really means is we need a language to talk about events in the space-time that doesn't depend on a choice of coordinates. That's going to make it inherently non-local, because it's only global relationships that can have a diffeomorphism invariant meaning. The value of the gravitational field at point t equals 3, x equals 4, and so has no meaning precisely because of diffeomorphism invariance. So given that, what are the meaningful questions? So, for example, the kind of thing Carlo referred to as relations among partial observables are an attempt to introduce these, what I'll just call for short, observables that are meaningful in the face of diffeomorphism invariance. And it's also an attempt to solve what's an equally important problem, is that it can happen that you can formally find such observable. I should say that in a quantum version, more people would normally expect, although I won't be quite using that language ultimately, but people would normally expect that these observables would be represented as self-adjoint operators in some sort of Hilbert space. The problem in that setting would be that not all operators, or in fact, the vast majority of them, would not represent invariant quantities. They would not be diffeomorphism invariant. So but it's possible that one could solve that in the sense of having a large supply of operators that were invariant. I should have said this first. We'll come back to this. You could imagine you found a large number of observables in whatever form you represented them, but you hadn't the slightest idea of what they meant. So the real observables that are of interest to us are ones that ask, for example, here's a space-time, it's starting off with some sort of matter collapsing. Did that matter form a black hole or did it not form a black hole? That's the kind of thing that we'd like to be able to talk about. And in that case, it's particularly clear that it has only a global meaning because an event horizon is only defined globally. But in general, that anything that's meaningful has this global character. So it's possible that you could have, so the second half of the problem is to find a large supply, ideally a complete supply of observables, and to understand physically what they're talking about. What do they have to do with the questions that we'd like to ask? Just to illustrate what can go wrong, and I claim does go wrong in the canonical quantization setting, in that case there's a well-defined formalism at a formal level anyway, in which one has the constraints, which I referred to before. The Hamiltonian is what's called a constraint in gravity. And the observables are no more than those, or no less or more than those operators that commute with the constraints. This natural symbol is my symbol to represent commutation. Yeah?
Local is a slippery word, of course. It can make different things. Classical generativity, which is certainly diffeomorphism variant, has been used to figure out the dynamics of the solar system with a very high degree of accuracy. Has been there's nothing non-local in that. If you think as non-local meaning globally over all over the universe.
I think it is non-local in this, but I don't mean physically I don't mean non-local in the sense of superluminal communication or something like that. I mean that the quantities one is talking about have to be defined by reference to more than just one point in its neighborhood in the manifold.
Okay. But not necessarily to the...
Not necessarily the full space-time, but yes.
Things are a lot easier in highly symmetric situations in the solar system to have a model as such. The problem of observables is principally for general geometry. It's very difficult finding observables. In highly symmetric cases, they're not.
You have a better head start towards identifying these well-defined invariant observables. So,
not symmetric at all. Also,
you mean it's nearly, by symmetric you mean it's near to, yeah, okay, yeah. I mean it does help that in the solar system we're not that far from a flat space-time, and we can use it as a springboard to construct sort of iteratively these observables. I think that's what you're saying. And roughly spherically symmetric. Well, Minkowski space is spherically symmetric, so being roughly Minkowski, and then even to a higher approximation, perhaps it's roughly spherical. Anyway, that's not even in that case. However, in essence, one cannot work, or one cannot actually work. The kind of things that people measure are time delays, radar, ranging, bouncing things, and those are whole processes. They're not just things at a given point. So you can't measure the gravitational field at a point in the way that you can measure the electromagnetic field at a point. That's all I meant. So in this case, you can at least formally produce a large number of observables if you understand the constraints. Even that is not so easy. But even once you have them, you don't know what they mean, because what they represent is essentially initial data for a solution of the Einstein equations. And to extract the meaning, you in effect have to solve the operator Einstein equations, and that's almost impossible. And in fact, personally, this difficulty is the thing that led me to abandon the canonical, in my own life, approach to quantum gravity. So there's a problem of principle flowing from diffeomorphism variance, a principled problem of time. The other class I call the technical problems flowing from diffeomorphism invariance. These won't have as much meaning to some of the people here, but let me, since I will be arguing that the path integral formulation is the best, most adequate one for quantum gravity, let's concentrate on that. When you do the path integral, you're adding up an amplitude for each four geometry within a given class. But when you add them up, you're adding them up with, this, of course, it's a continuum, a very complicated continuum of things. It's not literally a sum in the continuum case. And so you need some sort of background measure with respect to do the sum. You can't use counting measure, because if you count you get an infinite number. And that choice of measure is sometimes called the measure factor or the integration measure in the path integral. And it's notoriously difficult to define. Even in non-relativistic quantum mechanics, it's not a fully understood issue or problem, fully solved problem. In the language of canonical quantum gravity, this is connected, or almost, not quite the same, but it's closely connected to what they call the problem of defining the right inner product in canonical quantum gravity. To some extent, it's a problem of time only in the sense that time is continuous, and that produces a very large, very complicated infinity of things that you're trying to sum over. But there's also something that's specific to the kind of Lorentzian time that space-time represents, which is that the diffeomorphism group, even locally in some sense, is not compact. Unlike the so for those who are familiar with the analogous problem in gauge theories, there's the Faddeev-Popov procedure, for example, and that works better because the gauge group, although in a global sense it's not somehow, well, I shouldn't even say that. It works better because the gauge group at each point is a compact group, say SUN. And in a certain sense, that can even make it compact globally, if you were to use the Tikhonov topology, for example. But the important thing is that the diffeomorphism group is not like that. It doesn't have this character. That makes it harder to divide out by the volume of the diffeomorphism group. What do I mean by that? Well, if you sum over all if you sum over all metrics, if we go back to this picture here, and we sum over all 4 metrics in here, we're overcounting by an infinite amount because each metric can be subjected to a diffeomorphism. It doesn't change the physics, but it looks like a different metric on that given manifold. And therefore you'll get an infinite answer unless you, in some consistent way, divide out by that. And so I'm just mentioning that it becomes harder because of the non-compactness of the diffeomorphism group, which makes it somehow more infinite than it was in the case of the unitary gauge groups. Okay, so all of these can be seen as, these technical problems can be seen as problems of time.
What's the nature of the hardness of dividing out by volume diffeomorphisms? Is it like Gribov?
Yes, well, that's a good question. I don't think I could point. So for example, if you were to, so one might ask in lattice gauge theories, how do people cope with this? In the ordinary gauge theory, where the group is compact. In that case, you don't actually have to divide out at all. You just sum over all possible fields, and you are overcounting, but you're overcounting by the same amount at each point. And so it's just an overall factor, and if you just work with ratios of amplitudes, you never even need to deal with this problem. And here that sum won't even converge because you'll get an infinite number of, at least formally it would not converge. You'd get an infinite number of, an infinite volume locally that you'd have to be summing over. But it's a good question. So let me finish with my laundry list of problems of time by mentioning 3 more, the last 2 of which I think come closest to the main concerns of this meeting. This one, problem of time 4, is one of these that's kind of halfway in between a problem of principle and a technical problem. So I mentioned before that the path integral in the even in the non-relativistic setting is very difficult to define, and therefore it's also very difficult even in the setting of a fixed background space-time. By background we of course mean an absolutely chosen space-time that we give in the beginning of the theory and never modify after that. So that's a sort of physics jargon background. It means absolute. So even in that setting, it's very difficult. And in practice, what people do, the sum that you're supposed to do by summing over all the histories, doesn't converge. It has the character of a marginally convergent integral, like integral e to the I x squared dx from minus infinity to infinity. which sort of converges and sort of doesn't. If you give it, I noticed if you give this to Maple, if you put a plus sign here, you got an answer, and if you put a minus sign here, it's just a complex conjugate, you got infinity. So even Maple is confused about this integral. But it's sort of marginally convergent. What you can do is if you make time imaginary, even making it a little bit imaginary, the integral becomes nicely convergent in every theory, and that's called a Wick rotation. And that's true in every theory except for gravity. When you do this in gravity, the integral turns. So if it's not gravity, sort of flat space gauge theory or any field theory, it turns the integral into something that looks like e to the minus x squared dx, which is a nicely convergent integral. If you do it in gravity, it turns it into something that has, in certain directions, the character of e to the plus x squared dx. You can see that that's not a big improvement over what we started with. So, in a certain sense, you're forced to stay in the Lorentzian. And that's a problem, perhaps, well, because it relates to whether time can be taken mathematically anyway to be imaginary. One can think of that as a problem of time also. So I have a kind of question mark. Should we? I think it's fair to think of it that way. So let me finish this list with the two ones that are, I think, of the greatest interest here, which is the problem of becoming. Do things happen? I don't think I need to expand on that at all for this meeting, but just as a comment here that it's thought to become much worse if you don't have a unique slicing, and that's, for example, a unique foliation of space-time, and that's, for example, the motivation I think that George had when he tried to tell us how you could introduce a unique foliation. And this lack of the unique foliation is, again, an aspect of diffeomorphism invariance. The sixth problem, and last one that I'll talk about, is not really a problem. I've just put it here because it's an important aspect of time, but it's not something that we need to solve, unlike arguably these others, but it's something that we'd like to solve. Maybe quantum gravity will help us to understand the nature of the arrow of time and the origin of the arrow of time. So rather than a problem, I think in this case I'll call it an opportunity. So now in my introduction I said that these problems are largely resolved if we use a histories formulation of quantum mechanics and if the deep structure of space-time is discrete. Here just to help you remember and help me remember are the 6 problems that I identified. So let me review a little bit how people have approached the problem of quantum gravity, or in general how people approach the definition of a quantum theory, and then might make my little argument why the path integral is the most adequate one. So this is really asking, I mean, if you think about it, what you're really asking is, what is a quantum theory? How do we conceive of it? And there's different, basically 3, there are many ways people have thought about it, but there are basically, I think, 3, which are often thought to be equivalent in the context of, say, non-relativistic quantum mechanics, but may be very far from equivalent in the context of quantum gravity, especially with discrete space-time. Let me just review what they are. They're called the canonical formulation, the path integral formulation, and what some people call the algebraic formulation. The canonical formulation, I think, is the most familiar to people. You start off with conjugate variables at a moment of time, like Q and P. They're supposed to satisfy these commutation relations. They produce an algebra of operators. You identify among those operators one special one called the Hamiltonian that generates the time development of these operators, and so on. This quantum mechanics viewed this way is a kind of generalized Hamiltonian mechanics. In fact, the equations that you end up writing down, if you don't look closely, take the hats off the symbols and replace the square bracket with a curly bracket, which is the Poisson bracket, it looks almost identical to what you would have done classically. The second approach, the one that I'm favoring here, is the path integral or the histories approach. And this one performs some sort of sum over gamma here represents now, whereas Q represented, say, a position at a moment of time, gamma here represents the position at all moments of time. In other words, it represents a trajectory. In the case of quantum gravity, and if we stay in the continuum, it would represent a complete space-time, what sometimes people call a 4 geometry. The amplitude S, this is the classical action integral, you know, the integral of the kinetic minus the potential in mechanical case. And this is the quantum amplitude of that history. And this nu here, that's that that integration measure that I referred to before that has a problem to be defined precisely. But this is the form, so we're summing over a bunch of some well-defined class of histories or trajectories, generalized trajectories, and we're trying to make sense of this. And we have to do something with this. I'll come back to what exactly we do. But the point that I want to make here is that quantum mechanics viewed in this way is kind of, instead of being a generalized Hamiltonian mechanics, it's a generalized theory of stochastic processes. This e to the is, sometimes called a probability amplitude, is some sort of generalization of what in the classical stochastic theory would have been just a probability, which I think no one really understands the exact sense in which it is generalization. And to a certain extent, that could be said that that is the problem of interpretation of quantum mechanics from the path integral point of view. The third formulation is what I've called algebraic, and in that it generalizes what one does, say, in quantum electrodynamics, where one has an electromagnetic field at every point x. This x now is a space-time point, not just a spatial point. And this GAB is the gravitational field, the generalization to gravity of the electromagnetic field. And it has some equations that it has to satisfy, the Einstein equations. And you just put hats on those equations. In other words, you make them operator equations. So that's the point. That's the first half. And the second half is you have to introduce the more space-time analog or counterpart of the canonical commutation relations at equal times. And there's a way of doing that called the Peierls bracket that's kind of nice that I won't talk about anymore. I mean, there's just a technical thing. So just as the first canonical quantization makes quantum theory appear as a generalized Hamiltonian mechanics, the path integral makes it appear as a generalized stochastic process. I'm not quite sure to put here, but I put with a lot of question marks. Maybe it corresponds roughly to an operationalist point of view. Yeah?
For, say, particle physics, and done in great accuracy, both in terms of a reasonable amount of at least physicist rigor, and in terms of doing detailed calculations, it seems to me that what is employed is a mixture of canonical and path methods. So somehow it's easier, and maybe in some cases necessary, to use the canonical approach to more rigorously derive what form the final rules are to take, which then one does detailed calculations with far more conveniently in a path form. So somehow one is using 1 and 2 together there. And then the problem is if you're using just one of these things by itself, for quantum gravity, it's not clear.
Well, and it's not clear how to do 1 and 2 together in quantum gravity either. And the that's right. So you're saying that in this identified the problem of the integration measure. You're saying to a certain extent that's ameliorated by trying to bring it into connection with it, and that yes, sure.
And then unfortunately, it has both the problems that I was talking about and the ones that you're talking about. Detailed practical consideration may require a combined approach.
Well, maybe, but in the context that I'm thinking, it won't make any sense. So when we come to the space-time discreteness, there's really sorry. Okay, so this is all meant to be background to this problem of time. So why do I favor 2? And it's this Goldilocks kind of relationship. This 1, as we saw from the very beginning, has too little time. That's what the problem of time is. We have to recover time. So I don't need to expound on that anymore. 3, on the other hand, has, at the same time, too much time, but too much time of the wrong kind. It's pure gauge. So in this case, we have space-time because this x is a point of space-time. It has both t and x coordinate built into it. In fact, we do everything on a fixed manifold. So in that sense, we have time. On the other hand, this x has no physical meaning because of diffeomorphism invariance. So that's what I meant by calling it pure gauge. And when I say it has too much time, I mean that by choosing the manifold on which we work, we've forbidden the topology to change. And there are good reasons to believe that quantum gravity without the possibility of topology change is inconsistent. In that sense, 3 has too much time. And 2, of course, is just right. It works, this gamma is a space-time, so it doesn't need to recover time. It's working with something that has time in it. But also, it's completely free to choose, since the whole 4 geometry is dynamical, there's no background manifold like in this case. We're free to sum over different topologies, and so we don't run into that problem.
Don't you have to basically solve one of the Clay Millennium problems to have a rigorous definition of that path integral?
I would imagine you would, right? So that's why I'm going to argue for discreteness. Right? So in the end, the integral is going to turn into a sum. Yeah.
You mean changing the spatial topology?
Yes, if you like. Yes. I mean, the technical way of saying it that doesn't have to use those words is to say that the manifold need not be a product manifold of some space-like topology and the real interval, or R. So whenever that's not the case, we can say that the topology has changed. But I guess that, yeah, the word change, when used like that, kind of refers to a different space-like hypersurface having a different topology. Okay, so let's see so by introducing the sum over histories, how much have we gained with respect to these problems of time, if we still stay in the continuum. And 2 examples of approaches that go in this direction are causal dynamical triangulations and what's called asymptotic safety approach. This one is explicitly a path integral formulation. This one is trying to make gravity just look like an ordinary quantum field theory, so it's not unambiguously in the path integral formulation, but in practice that's what it tends to be. So what about the first problem of time, that of recovering time? Well, as I just argued, that's solved. There's nothing to recover. And I should have said here almost. We could almost stop the lecture here because that main problem has been solved. How about the second problem of time, which is the problem of observables? That's a different story. It's perhaps easier to come up with the observables with invariants of the geometry of the metric which are meaningful in the face of diffeomorphism invariance. But it's not still so easy. Even these classical cases that people refer to, like the solar system, it's not at all trivial. But it's certainly something, you're better off than when you have only data at a moment of time, like in the canonical approach. So you can probably think of some observables anyway. Maybe enough, maybe not enough. And as far as problem of time 3, the diffeomorphism, I don't think actually that I don't think you've gained all that much, but maybe something in this case. It's still subject primarily due to the continuity of time that it becomes all these same technical issues that I referred to in the path integral. I mean, they're still there in the path integral. In fact, in non-relativistic quantum mechanics, they're actually worse than in the canonical formulation. In quantum field theory, I think it's arguably at the same level of difficulty. Now, what about so let's suppose we take decide we're going to use the path integral formulation. I just want to make a couple of remarks on the conceptual tasks that are set for us when we do this. See, in the case of a canonical formulation, the answer to a quantum theory might be it's a specification of a wave function and some algebra of observables and a Schrodinger equation for the evolution of the wave function. We saw that that's not going to work in that form in quantum gravity. But that's the kind of answer you would give in a non-relativistic setting. What is the corresponding answer in the path integral setting? The problem is we don't fully know. And this, as I said before, is, I think, the problem of interpretation in from the standpoint of a history's formulation. Usually when people talk about a path integral, they interpret it as a propagator from one moment of time to another, or one hypersurface to another, how to get psi from the initial hypersurface to the final hypersurface. But the interpretation is then thrown back on the wave function, and you've gained nothing from a philosophical or a interpretive point of view. What we really need to do, I claim, I want to urge, is to free the path integral from that interpretive crutch. We want to be able to talk about what it's saying about the world without ever referring, except possibly as a technical device sometimes, to a wave function. Attempts to do this are the decoherent histories approach and the idea of a quantum measure, which is closely related. I won't have time to say anything about them, but I think that it's actually, not everyone certainly agrees, but I personally believe that this is almost an inseparable problem from the problem of quantum gravity more generally. Okay, so I'm running out of time, so let me skip. Just highlight this for those experts. There's a question of what is the continuum, even if we think in the continuum, what is the decoherence functional for gravity? For those to whom this has meaning, the decoherence functional is written as an amplitude for a pair of paths, an amplitude for one, the complex conjugate for the other. That's e to the is. But there's a final delta function that comes in the usual formulation. What is the counterpart of that in quantum gravity? I think that's a crucial problem which can be addressed no matter what your point of view is on quantum gravity and is worth thinking about. However, aside from recommending that problem, I want to devote the rest of this talk to how these problems appear in the context of sequential growth dynamics for causal sets. This will bring us back to the problem of becoming, ultimately. So unfortunately, to do that, I have to describe what is a causal set. I think Faye is going to do that in much more detail, so I'm going to try, although it's not quite logically proper to do this, I'm going to just try and skip over most of it, since there's only like 5 minutes left, I guess. The main thing about a causal set is that it's an atomic or a discrete replacement for space-time. By being discrete, it helps to cure these problems in infinite integrals, because now we're just doing sums. But it's a discrete structure of a very special kind, which is called a partial order. And because it has that special kind, it allows us to explain why there's a metric why space-time in the continuum approximation has a metric, and specifically why that metric has to be Lorentzian in signature, why a partial order cannot produce a Euclidean signature metric, or Riemannian metric as people call it. This whole approach flows out of a tradition that's almost as old as relativity itself, in some senses older, which is the tradition that of all the structures of space-time, the causal order is the most fundamental one. And in a way that I hope Faye will explain a little more in detail, the basic data that the causal set carries, which allows us to reconstruct a geometry in certain cases, is the order relation, which is the causal order relation, the temporal order relation of before and after, and the fact that it's discrete, which allows us to count. So there are technical reasons to like causal sets, but from a philosophical point of view, I think this, to me, is the strongest one, is it explains to us the origin of geometry. The technical definition of a causal set, this being a nickname for causal set, quaset, is a past finite partial order. I won't try and define it, but what it means, it's a set of elements, you could call atoms of space-time, with a kind of ancestral relation among them, and to say it's a partial order is just that it has the properties of an ancestral relation of parents and children, or descendants and ancestors, and technically they're called transitivity, acyclicity, and local finiteness. In fact, I'm going to take it past finite. In the cosmological setting, we're going to assume that no element has more than a finite number of ancestors. Okay, so this is kinematically. What is a causal set? What is the dynamics that we're talking about, the dynamics of sequential growth? This is going to bring in the notion of passage, if you like, or of becoming. This becoming is going to be understood as a growth process. So I'm going to describe for you a definite dynamics, although I won't have time to describe it in very much detail. But it's classical. It's classical and it's stochastic. Remember I said that quantum mechanics can be viewed from the path integral point of view as a kind of generalization of a stochastic process. This is kind of the classical limit of it, if you like. It is a stochastic process, and it embodies the idea of growth, and we'll see that it embodies the idea of growth completely, arguably, compatibly with diffeomorphism invariance, or general covariance, I should say here, which amounts to label invariance. So let me just give you a picture, just to give you a sense of what a causal set might look like, a little more realistic one. This represents a portion of two-dimensional space-time. What's drawn here are the links, the causal links, that is, the parent-child relationships. There's many things I could say about that, but let me just point out one thing. Almost all of these are at 45 degrees here. What you're seeing is the light cone structure, or the role of the light cone in a Minkowski, or in a Lorentzian signature space-time, in this case Minkowski space. What is the growth process? So the growth process starts, if you like, cosmologically starts from nothing, right? So we have here the empty causal set with no elements. It's a succession of bursts, as I said. So the first element is born. Well, there's not very many causal sets with only one element. So you get this, right? Now the second element is born. Now there's already two. The two elements can be parent and child, or they can be just sort of unrelated to each other, causally. Suppose that the second one was born as a child of the first. Then you're following this path through this. What I've drawn here is itself a poset whose elements are themselves causal sets. Then the third element is born. Well, let's say this is what happened with the second. Then there's three choices in the way that the third element can be born. It could either be a child of the child, like a grandchild of the original one, or it could be, like here, a sibling of the second one, or it could be here completely unrelated. Notice also that if I go here, I could have got there another way. I could have imagined, which amounts to imagining that this element here is born before this element here. I'll have the picture again, a little bigger. And that ambiguity needs to be, it has no physical meaning. It's just a labeling ambiguity. And we need to make that disappear out of the physics in order to realize general covariance. Okay, so I think I may have to skip almost all this slide. So what the growth process appears as in this setting is just a random path through this diagram, this poset of causal sets. And the dynamics is specified, just as with any stochastic process, which is, if it's Markovian, by transition amplitudes from one node to the possible subsequent nodes. The fact that it's Markovian is actually a consequence, although I don't have time to say it clearly, of the coordinate of the general covariance, the label invariance.
Rafael,
Yeah.
just want to make sure I understand this diagram. So on the previous slide.
Okay.
So the dark arrow, the bold arrows are parent-child relations.
Oh no, the bold arrows are just, they represent one particular path. They have no meaning. Yeah.
Okay, so the arrows are all parent-child relations.
They're all, well, they're not all. They always include at least one parent-child relation, but it can happen that the new element is born with. Yeah, no, I think it's fair. But the point is, it can have more than one parent. That's all. So in general, it'll choose a large number of parents, not just a single parent. So, for example, I don't know if there's an example. Do I have the next one? Have any? Here's an example where we had these 5 or whatever it was elements already born, and then when this is born, here it has 2 parents, And in general, it can have an arbitrary number of parents.
When you say it's Markovian, you mean not with respect to the time that's inside of those sets, but that's with respect to the dynamics?
Absolutely. It's Markovian with respect to this artificial, this parameter time, which is not meant to have any physical reality, except to the extent that it's reflecting the internal relationships. And it's that necessity to deprive it of any further physical significance that corresponds to general covariance. Okay, so there's a formula. This idea of general covariance, which we've sort of discussed. Let me just look ahead and see how many more slides I have. Okay, only 2 more. So this is, I've tried to illustrate the thing that I was saying in words here. So consider a set of 3 bursts which could have gone this way or could have gone this way, arriving at the same causal set. So here it is shown again. That corresponds, here's the causal set at which we've arrived at this partial stage of the process. And those 2 pairs correspond to different labelings. So in one, there's a third labeling that I haven't shown that it's also possible, but in the one of them, this element was born first, this one was born second, unrelated to it, and then this one had a child, the third one. In the other way, which is the one I showed, this one is born first, it has a child, and then another one is born unrelated. This corresponds, if you like, this is the counterpart in the causal set of a different slicing of a continuum space-time, and we want it not to have any physical meaning. That means that the probability to arrive at this ought to be the same as the probability to arrive at this. That's how we are going to implement the idea of general covariance as label invariance, and it can be seen with a little thought that it's the same as path independence in that diagram that I had before, path independence here, and it also makes the process Markovian in that auxiliary time parameter. If you put that together with a certain causality condition, which we call Bell causality, that tells you somehow that the influences don't propagate in a way not allowed by the inherent causal structure, you get a unique family of dynamics. I'll give you a second to just look at this if you want. This represents a binomial coefficient, this parenthesis. This pi here is the total number of ancestors that the new born element has, and this m is the total number of its parents, immediate ancestors. And if you really want to read it, you have to, there's a typo here. This m should have been a sum over L, not a sum over m. Here's an illustration of a particular burst, and for a particular choice of parameters producing what's called transitive percolation, this is the probability, the transition probability of that particular burst happening. That is, of this element being born with these 2 as parents and...
What's Tm?
Which one?
T.
Oh, T, that's the free parameter. So there's a sequence of free, that's a non-negative parameter. That those are different dynamics within the same family. All of these, in a way that I can't describe now, are rather simple, mild generalizations of this transitive percolation, which I haven't also described, of course. So now so now let's come back to the 2 questions of main interest, I think, here. How does it solve the problem of time 3? Those were the technical problems. Well, that was sort of telegraphed and sort of it's the motivation of many people for doing discrete space-time, is that the path integral becomes now just a sum. So that's sort of self-evident. In what sense it solves or makes much better the problem of time. How about the problem of time 6, which is the arrow of time, the opportunity for quantum gravity to bring us new insight into the directionality of time? Does it solve? I think in a sense it solves it by rendering it trivial. In other, because in the kind of boundary condition we've chosen here, the causal set that's, if you let the process run to completion, so to speak, run to infinity, you'll produce a causal set that every element has a finite number of ancestors and an infinite number of descendants. That's clearly not time reversal invariant. And so it just through a boundary, that's why I compared it to this, whatever it was called. there's a subtlety here that I could mention, should mention, which is that in certain special cases of these classical sequential growth dynamics, you can embed them in a slightly larger probability space in which a time reversal invariance does come back. But even if you do that, they're the exception. So for almost all of the choices of the parameters of the dynamics, that doesn't happen. So in one or both of these ways, I think we could say it maybe is solving the problem of the arrow of time. Okay, you had a question. I have 0, so maybe, is it an urgent question?
The problem is whether growth itself already implies the arrow.
Yes, I would.
The growth and decline, birth and death at the same time in the process. So only the living members.
Well, that's a very good question that always comes up. Ask it to me again at the end. But I should say that the process as it's defined does not provide for death. It's only birth. It's a birth process. How about the problem of time 2, the conceptual problem of the need for observables to identify questions that we can ask, if you like, predicates about the causal set that have a clear physical meaning. Let me just say what the predicate is that you can what the class of predicates is that you can identify. See, like in a space-time, you might ask, does it have a black hole in it? Of course, that's a very high-level question. But the claim here is that all such questions, which are meaningful, not depending on a particular labeling, can be made from much simpler questions, which are what we call stem events or stem predicates. And the question is, take your favorite finite causal set and ask whether the actual causal set contains that finite causal set as a subset which we call a stem. In other words, it contains all its ancestors. So is it realized within the actual causal set as a stem? So in this case, the causal set of interest is the lambda causal set. It's a 3-element causal set called lambda for an obvious reason. And we see here that it is contained as a stem. On the other hand, if we ask if the 2-chain, which is just this, if that's contained as a stem, the answer is no, it's not, because where would it be? See, here's a 2-chain, but it doesn't contain all of its past, all of its ancestors, so it's not contained. So the point is, for all possible stems, if you answer yes or no, whether they're contained, first of all, you know what you're asking about physically, what it means, and second of all, you've got a tremendous amount of information about the causal set. And in some measure-theoretic sense, in the context of these CSG models, classical sequential growth, you have all the information. So every question, you have a complete set of observables, if you like. And since it's all happened at a kinematic level, arguably, it'll go through in quantum gravity too. So I think that's a big progress conceptually. We've solved that problem of time. And let me finish with the, let me finish with the problem of passage or becoming. So as you said, I think was said already, the time passing has a correlate in this story, which is the birth of elements of the causal set. And yet, general covariance is respected. It's what's happening here, if you like. I mean, you just have to think about it and see whether it's satisfactory to you. But what's happening, if you like, is that a metaphor has been traded for another metaphor. Usually when people think about time, passage of time, they think of a moving present. They think of the past converting into the future at the present or whatever. I don't know, whatever language you like to use. But it's a metaphor of motion. In space-time, it's a hypersurface moving through some space-time. And then it looks like you already had the space-time, which is the black universe. And that doesn't seem satisfactory. Here, what's really happening is we're changing the metaphor. I mean, we're doing that for a reason, because the process as it's described, the dynamics, corresponds to a different metaphor, which is the metaphor of growth. So we're talking about a process which is always incomplete, and which is laying down the past as a kind of sediment. And in some sense, that sediment is what exists, and there's no present. There's nothing moving. There's a process, but there's no present. There's, if you like, a past and a not yet existing future. You might give the, just to help think about it, sometimes it's useful to give it a name. So I would say that there's a notion of becoming here, but it's a different kind of becoming, which I'd like to call asynchronous becoming. And that's what I would submit as the resolution, or the way in which becoming can be made compatible with general covariance. I mean, I remind you that I didn't have time to describe it in detail, but there's a technical thing that makes this, although that makes this asynchronous, that is, it makes the physical implication of the labeling drop out of the physics. So with that, I'll stop.
So we have time for one or two quick questions. I don't know who was first. Edward, it must be brief.
If you are replacing time reversal invariant laws by a more fundamental thing which is based on a directed process, of course that's birth or death, and how can you expect to recover the suitable limits of time reversal invariant laws in such a physics?
Well, that's really asking, let's limit ourselves to gravity. So there's two aspects. One would have to do with quantum field theory in the space-time, and the other one would be quantum gravity itself. So this is, of course, in the case of gravity itself, what we basically know is classical gravity, which is the Einstein equations. So what you're really asking, I'd like to translate it as how can we expect to recover the Einstein equations from this kind of dynamics? That's quite a long story, but in there is a very central difficulty, which is recovering any local physics. If you can recover approximate locality, then sort of renormalization group arguments, basically just dimensional arguments, strongly indicate that you would get the Einstein equation. So I would translate that into a different question. How can we expect to get anything like a manifold, and how can we expect its dynamics to be described by an approximately local Lagrangian, local action principle? That'll be another talk, so I'm sorry not to give a more definite answer.
There were two questions here.
I would like to ask in slightly more detail what your interpretation would be for an element of a causal set. Is that a region in space-time?
It's a sort of atom of space-time. I'd call it an atom of space-time.
Atom of space-time. And so the birth relation would then be a creation of some new atom?
Yes, it's a new atom coming. So the idea is that there's like in the 1 second that we talk here, in 1 cubic centimeter, I forget the number, but it's something like 10 to the 139 births have taken place of these atoms.
The parent-child relation is like being in forward light cone?
The ancestor relation is like being in the forward light cone. Right? Parent-child, which is what we call a link, a kind of irreducible causal relation, is a little closer, but not quite the same as being on the light cone. And then the ancestor relation is just being somewhere in the future.
So I'm not getting how you can have both general covariance in your sense of this relabeling and time passing as a birth of elements of a corset. So I mean, the diagram you had with the 3 dots, 2 dots there, 1 dot there, reminded me of DHS duality in particle physics, where you can either view a process as 2 particles coming in here, exchanging a particle and going out, or 2 particles coming in, forming a bound state and going out there. And then there was this problem of double counting that process in hadron physics, right? The idea was to identify them. So don't you have the same thing happening in your case? So you can either view it as these 2 particles coming in and forming, giving birth to this element here, or these 2 atoms of space here and giving birth to this one here. So, I mean, in which direction are these things being created if you have this?
Well, locally, so that's hard. I think I'd like to, and what I'd like to say at this point, and see if it helps or not, is that you're trying to see it from outside, a sort of God's eye view of the process. And that's bound to fail. You have to think of it from inside, which is what we actually are. There is no God's eye view. From the point of view of any particular, say, parent-child relationship, one is first and one is after. So that's the notion in which there's growth, in which there's change. But now you want to ask, which is it? General covariance is supposed to tell us it's neither. I mean, neither one, it's either, if you like, or it's neither. The only objective relation is the parent-child. It's the thing that's built into the structure of the causal set that's created by this process. The choice of which one is first is supposed to be physically meaningless. That's the intention of this word asynchronous becoming. It's like a tree growing. It's like a tree growing at its tips, and you can't really see if a leaf appears here and a leaf appears here. You can't really say which one has happened first if they're space-like separated.
So we have like 4 questions in line. In principle, it was not allowed, but if you promise to be telegraphic, then we can give it a try. So there's Nick first, then Wayne, then Carlo, then David.
Handily, I mean, you started to answer it. I just need to, because there's sort of a follow-up now to it. So say things are, I mean, to be asynchronicity, that's the word, is a relation. So I guess I was having a hard time seeing what are the things that are related. So is it that we have becoming sort of in their sort of external time, but there's no becoming that doesn't map into the sort of internal?
That's what's asynchronous is the growth that's going on sort of over here and the growth that's going on over here. So it's used in the same sense as, say, in computer science, where you have asynchronous processes running. So something forks off 2 processes, each one runs in its own time, but they don't have any particular causal relationship to each other until some third process needs the output from both of them. So that's the sense of ace. I'm using it in that same sense.
That's right. The 2 places here are in the poset and the posets, right?
No, they're in the single growing poset, the causal set. They're 2. So think of a tree, which is a special case of a causal set. So a new bud appears over here, and then on another branch, a leaf grows or something like that. Those 2 events are asynchronous. They're happening, but they're happening asynchronously.
I'm trying to get clear on what this process of growth of the causal set is doing in order to get becoming or an arrow of time in physics. And here's one way to put it. I mean, I think you said that the growth order is in some sense non-physical, and temporal orders in the causal set are given by the ancestral relationship. Then it seems to me that instead of thinking of a growing causal set, I could go blockhead, and you give me a Markov process by which causal sets grow, and I can just think of that and say, okay, I've got this, I've got this probably measure with the space of all possible completed causal sets, and within each one of those, there's going to be these directed arrows, but then it seems that those 2 ways of thinking about them are entirely equivalent. But I mean, if one has becoming, the other one ought to too. But so what's the process of growth doing in terms of actual physical becoming?
Well, it's generating the causal set, but you're absolutely right. There is a mathematical version of the stochastic process in which one works only with these completed causal sets. And
then am I lacking becoming in that?
Yes, because then you're talking about the probability of having produced something, and you've thrown away the process. That would be the point of view. You've thrown away the process that produces it. But that's kind of philosophical. But what we could say more concretely.
The physical relations of ancestral relations, which are the physical temporal relations, are the same in both cases.
Yes, that's right. Except in one case they're all built up, and in the other case they're in the process of being built up.
I'd like to know.
But I'm sorry. The point I wanted to make is that this stochastic process is described just mathematically more naturally in terms of transition probabilities. Okay, that's it.
There's been a lot of discussion in this meeting about the block universe.
Block universe.
With the problem formulated, I mean, there's Newtonian physics, or for that matter, classical general relativity, and the question whether this mathematical picture accounts or not about the canon, as one could imagine is not accounted for our phenomenological perception of becoming, the difference between here and now. Now, the question is how this temporality that you put in quantum gravity relate to this problem. Namely, you're going the other way. You're going to say the classical Newtonian or general relativistic, classical general relativistic description, it's an approximation of something which is behind, which has a temporality in it, stronger in some sense. But are you saying that it's not true that quantum gravity is well approximated by classical physics, and therefore, in some sense, my own perception knows about this quantum gravitational. There is a channel through which I know more than classical physics macroscopically. I really know about some quantum gravitational phenomenon happening down there at times.
Well, yeah, so that point came up also yesterday in a forum. If the structure of reality is to be growth in this sense, then I suppose it's also manifested at a macroscopic level, but it's much harder to pick it out. So I think one could take the point of view, even if there's a continuum space-time, that it also proceeds by growth. It's just very hard to imagine what that means. I mean, if it grows just a little bit, that's an uncountable number of points that you've added. It's very hard to sort of form an image of it in the way that we can in this discrete case. But one point of view, I don't have myself a definite answer in my own mind to your question, but I'm drawn to the belief that yes, our sense of time passing is in some indirect way a reflection of this growth, dynamical growth process. And with the aid of this, if this is how nature is, with the aid of deeper understanding of space-time, or if this is not how nature is, with the aid of this as an example of what it might have been, maybe we could go back and reconceive even continuum macroscopic space-time as a kind of growth process. And maybe that's what we're picking up. But I couldn't say, I don't want to push that.
So, very last question, more than telegraphic.
Maybe I should say that. Maybe I can just put it on the table.
Okay.
There's something very basic that I'm missing somewhere. You were talking about, standard becoming models of sort of the space, the upper boundary of what exists so far, pressing forward. And you said, rightly to my mind, it's not clear what's going on there because we're assuming a sort of place for it to push forward into. We're assuming a framework against which we can judge it to be pushing forward. Were you thinking when you said that of this growth process that you're describing not having a problem like that, or was your talk about shifting one metaphor?
No, that's right. I'm thinking that it does not have that problem.
So why? I mean, why is it the case that just in a very flat-footed pedestrian way, you talk about growth, you talk about birth. It sounds like you're assuming a temporal framework behind all this, in which you can talk about things like growth.
Right. So the magic words are background independence. If you accept that what we've done is produced a background independent model or type of growth model, then I think you should be happy. And I think your question is this parameter time or this label time in which the growth is happening a kind of implicit background I mean, we don't have in that first picture I showed, there was a whole four-dimensional manifold. That's certainly not there, but there might be a remnant of just this parameter time.
Right.
Is it happening in that?
Right.
And my claim is that formally it is, yes, but that extra time is gauge. And that's the point of these general covariance relations. That extra bit, the bit of that parameter time that does not reflect the inherent causal relations
Right.
of the causal set is pure gauge.
Right.
If you're willing to be convinced of that, then I think that should allay your doubts.
So remember that there will be another causal set based talk afterwards, so you can ask more questions.
Okay.
I don't know if there was
Okay, good.
microscopic. And
Oh, okay. No, let's finish because we've only got 10 minutes.
let's thank the speaker again.